Welcome to True Projects. In this video, we are going to explain about efficiently mining frequent item sets on massive data. Introduction. The project addresses the issue of efficiently mining frequent item sets from enormous data sets. Frequent item set mining is a critical procedure that returns all sets of items in a transaction table whose frequencies exceed a predefined threshold. Due to high input cost and complex data structures, existing methods for frequent item set mining cannot efficiently compute frequent item set on enormous data. The project presents a novel pre-computation based frequent item set mining (PFIM) technique that divides the transaction table into two parts: a big old table that stores historical data and a relatively small table that stores newly created data. PFIM begins by pre-constructing the quasi-frequent item set on the old table whose supports are greater than the lower bound of the practical support level. PFIM, given the provided support threshold using the quasi-frequent item sets, PFIM may shiftly return the required frequent item sets on the table. When the tables are combined, the project includes 3 pruning rules to lower the size of the involved candidates, as well as an incremental updating strategy to efficiently reconstruct the quasi-frequent item sets. Extensive experiments findings reveal that PFIM outperforms existing methods and runs 2 orders of magnitude quicker than the most recent approach. Objective. The project's objective is to offer a novel pre-computation based frequent item set mining (PFIM) technique for effectively computing frequent item sets on large amounts of data. The project attempts to address the limits of existing methods that require multiple pass table scans or the construction of complicated data structures that exceed the available memory on large data. The PFIM algorithm divides the transaction table into 2 parts and pre-constructs the quasi-frequent item set on the old table whose supports are greater than the practical support level's lower bound. When the tables are combined, the project includes 3 pruning rules to lower the size of the involved candidates, as well as an incremental updating strategy to efficiently reconstruct the quasi-frequent item sets. The result of the experiments reveal that PFIM has a considerably advantage over the previous algorithms and is 2 orders of magnitude faster than the most recent algorithm. Requirements. The requirements of the project are hardware requirements and software requirements. In hardware requirements, we have operating system Windows only, processor i5 and above, RAM 4GB and above, hard disk 20GB and above. Software requirements. In software requirements, we have Python IDEL with 3.7 version. Methodology. To implement this project, we have designed the following modules. The first module is Upload Dataset. This module involves loading a large dataset into memory. The dataset typically contains transactional data where each transaction consists of a set of items. Each transaction can represent things like purchases by customers or actions in a game. Second module is A priori algorithm. The a priori is a classical algorithm used for frequent item set mining. It's designed to find sets of items that frequently appear together in transactions. The algorithm works by iteratively generating candidate item sets of increasing length and then scanning the dataset to determine the support of these candidates. Item sets that meet the minimum support threshold are considered frequent. The process continues until no more frequent item sets can be found. Third module is PFIM algorithm. Pattern Fragment Incremental Mining. PFIM is an algorithm developed to address the limitations of a priori, especially for very large data sets. It focuses on mining frequent item sets efficiently by identifying and mining patterns within item sets to reduce the search space. PFIM involves breaking down large item sets into smaller fragments and incrementally mining patterns from them. This can improve the efficiency of mining, especially for datasets with a high number of items and long transactions. Fourth module is Execution Time Comparison Graph. To compare the execution times of the a priori and PFIM algorithms, we can perform the following steps. Implement both algorithms or use existing libraries that provide their implementations. Load the dataset into memory. Run both algorithms on the dataset and record the execution time for each. Plot a graph that compares the execution times of the 2 algorithms. The x-axis represents a different dataset size and y-axis represents the execution time in seconds. Execution. For the execution of the project, we need to open the code folder. This is the code folder, this is the dataset folder. To implement this project, we have used COSAC dataset. This is the main code file. This is run.batch file. Instead of executing our project in the command line interface, we have created Windows batch file to execute the project. Double click on run.bat file. This is the graphical user interface which we have created using Tkinter library. Using this GUI, we will interact with the project. So in the upload dataset, we need to upload the dataset by browsing it. So click on COSAC and open it. So here we can see that the dataset is uploaded. Now in the minimum support, we need to type a number. So I am giving minimum support as 5. In above screen, I gave minimum support value as 5. And we can give anything above 5. And if you give below 5, then dataset has large amounts of transactions. So it will take large time to compute all patterns. Now click on run a priori algorithm to run a priori algorithm. In above screen, we got frequent patterns for a priori algorithm. If we scroll down, we can view all the patterns. In above screen, we can see a priori it took 183.88 milliseconds to find all frequent items. Now click on run PFIM algorithm to run PFIM technique. So here we can see the total number of transactions in dataset and frequent patterns found in the dataset. And in above text area, square bracket contains item name and outside of square bracket contains value represents support value. If we scroll down, we can view all the patterns. Now click on execution time comparison graph to get the graph. So this is the graph. X-axis represents the algorithm name and Y-axis represents execution time by those algorithms in milliseconds. Close the graph, close the GUI, and the final conclusion of the project is the project concludes that the suggested pre-computation based frequent item set mining PFIM algorithm is an efficient way for computing frequent item sets on large amounts of data. The PFIM algorithm divides the transaction table into two parts and pre-constructs the quasi-frequent item set on the old table whose supports are greater than the practical support level's lower bound. When the tables are combined, the project includes 3 pruning rules to lower the size of the involved candidates as well as an incremental updating strategy to efficiently reconstruct the quasi-frequent item sets. The experimental results reveal that PFIM outperforms existing methods and is 2 orders of magnitude faster than the most recent approach. As a result, the project finds the PFIM algorithm is a promising solution for frequent classification.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.